Hey guys, it's me again, Devanshu Upadhyaya, and I'm back with yet another question from the Erst Goel 30 Days 6 Company Series Challenge. We have already covered 4 questions from this challenge from the Microsoft section, and today I will be covering the 5th question from the Microsoft section, which is envelope and dolls. This is a little good hard question and it has been asked in Google, as you can see from the tag here. So I will be sharing my approach and intuition, and I will be coding it. So I will be solving this question in this video, and we will cover more question in the next video, and like bulls and cows, another question. Because the series is very because the series has 90 to 100 question, so it will be really difficult for me to post a single question every video. So I'll be posting two questions or maybe three questions, at max three questions in a video. But if its question is a difficult question, or it is a medium question but it has a good requirement of intuition behind it, I will be covering it in a single video. Like this question, I will be covering this question in a single video so that I can share my intuition and approach. So without wasting any more time, let's jump into the question. So the question states, you're given a 2D array of integer envelope where envelope I equals to wi comma hi represent the width and height of an envelope. Basically, they are saying wi and hi are the width and height of a particular envelope. One envelope can fit into another if and only if both width and height of one envelope are greater than the other. So basically they are saying, let's say 5,4 is an envelope and it can only fit into 6,7, not in 6,4, because 4 and 4 matches, right? Because they are both same. So for an envelope to fit into another envelope, both its width and height should be smaller than the width and height of the bigger one. Okay. Return the maximum number of envelopes you can Russian doll. Basically, what is a Russian doll? Let me show you what is a Russian doll. Oh, okay. So this is a Russian doll. You can keep one doll into the another, and this is what a Russian doll is. So return the maximum number of envelope you can Russian doll. That's why they have given it a name Russian doll. You can not rotate an envelope. So you cannot rotate an envelope so that the width becomes the height and the height becomes the width. You can't do that. If you're thinking that I have this rectangular envelope, I can rotate it, and this will become the height will become the width and width will become the height, and I can now put my envelope. No, you can't do that. So if you guys are familiar with one question which is LIS, that is longest increasing subsequence, this question looks similar to it. If you guys are not familiar with LIS, in LIS what we do, let's say we have a 3, 4, 4 and 7. Let's say we have this uh, let's say we have 3, 5, 4, 7. Okay, this is better. We have 3, 5, 4, 7. We want to find the longest increasing subsequence. There can be multiple subsequence which has a increasing, which are in the increasing fashion, but we need to find the longest increasing subsequence such that the next element is greater than the previous one. So this is called longest increasing subsequence. This can be solved using two things, that is DP and binary search. How we did with binary search, I'll talk about it. But the process with DP is, let's say I'm standing at 3. I have no previous element, right? So we can say DP of IDX comma previous element. So 3 has no previous element, so we'll put as 3 as the only element. So DP of IDX comma previous equals to 1. And then we'll move to the another index. Let's say we came to 5. So the previous index now was 3. We change the previous index to 3. So at this point 5 is greater than 3, right? So we'll just add it into it. So the DP of IDX plus 1 will becomes 2. So we'll move to another 4, because now the previous index was 5 and 4 is smaller than 5, so we can't put this into it. Then we'll come to 7, and yes, 7 is greater than 5, so we'll get it to 3. So the recurrence tree will look like something like this. Let's say this is 3 comma 4 comma 3 comma 5 comma 4 comma 7, 3 5 4 7. So we have two options. either to pick 3 or not picking 3. So we picked it. Then when we come to this index, so we have the option of picking 5 if it is because we have now because now we have a previous element. We will check that is it greater than 3? Yes, it is. So we have an option of picking it and non-picking it. So we'll pick it. So let's say we picked it. Then we came to this index, and then we will say 4 is smaller. So we have only one option of not picking it. So it will be again 3, 5. Then we came to this index, and we have an option of picking it. So we picked it, and we came 3, 5, 7. Then we'll go back, and we have another way of not picking it. So 3, 5. So 3, 5 is also a subsequence which has an increasing fashion, but we will not consider it because we have a 3 size array. Then this will go back to this one, and at this point, because 4 was smaller than 5, so we don't have another option. So we'll cross it. This will go back to this one, and there was an option of choosing 5 or not choosing 5. So we will not choose it, and then we'll come here. Now previous element is 3, so we can pick 4. This will become 3, 4. And then there is a chance of picking 7. Yes, I can pick 7 because it is. So 3, 4, 7 is another subsequence which has a increasing fashion, or not picking it. So it will be 3, 4. 3, 4 is also one of them. But the size of 3, 4 is smaller than 3, 5. So the recurrence tree looks like this. So this is a way of founding LIS. So can you guys see the similarity between these two ways, like LIS and this one? The only problem is we need to find the maximum increasing, longest increasing, not subsequence. We don't need to find the longest increasing subsequence, but we need to find the longest increasing subset. What is the subset? A subset is nothing but, let's say we have 1, 2, 3, 3, 2, 2, 1, 3, 1, 3, 2. All these are subsets. But 1, 1, 3, 1, 2, these are subsequence. 1, 2, 3. These are subsequence. Subsequence are created by deleting one of the elements without changing the order. But in subset, we can change the order. So basically, we need to find the longest increasing subset here. So a longest increasing subset. So if we have this array, let's say we should paste it again. We have this array. We just need to make sure that it is in a fashion that we need to create so that we can apply our longest increasing subsequence thing here. So we can apply that algorithm here, because in longest increasing subsequence we cannot pick 2, 3 and then pick 4, 5 because that will break the subsequence. So what is the solution of this? The solution is simple. We just need to sort it. That we get a subset in such a way that it also follows the algorithm of longest increasing subsequence. Basically, I'm saying, let's say there is an array 3, 4, 7, 8, 2. If our question was demanding pick 2, then pick 3, then pick 4, then pick 7, then pick 8. Our envelope question was demanding this. But the LIS will do pick 3, then pick 4, then pick 7, then pick 8, but can't pick 2 because 3, 4, 7, 8, 2 is not a LIS, longest increasing subsequence, because 2 is smaller than 8. But 2, 3, 4, 7, 8 is a longest increasing subset. That's what I'm talking about. Just need to sort the entire envelopes array. So we'll sort the entire envelope. So let's sort it. It will become 2, 3, 5, 4, 6. Now 6, 4 and 6, 7 both have same width. So the default way of sorting, if we just apply the sort algorithm, it will check if both this element are same. If both the first element are same, it will sort them on the basis of the second element. So 6, 4 will come before 6, 7. So we got this array. Now let's look for our DP method. So we pick 2, 3. Can we pick 5, 4? Is it matching it? Yes. 2 is smaller than 5, 3 is smaller than 4. So yes, we can pick it. So the previous element is now 5, 4. Can we pick 6, 4? No, we can't, because 5 is smaller than 6, but 4 is not smaller than 6. So the previous element stays 5 comma 4. Can we put 6 comma pick 6 comma 7? Yes, we can. So the previous element is now 6 comma 7, and the size becomes 3. The DP method is quite logical, but the only problem with the DP method is this is O of n square. Why it is O of n square? Because we are keeping the track of the previous element also, and the size of previous element can go from I to n. That is, our 2D DP is nothing but I comma n. The iterative approach saves the space. There is an iterative approach of this DP which saves the space. We only do DP of I, but the time complexity remains the same, that is O of n square. So O of n square is not acceptable here. We can check it because it's 10 to the power 5, and if we do O of n square, it will be 10 to the power 10, which is not acceptable. We need a solution under the range of 10 to the power 7. So I was talking about there is another way, which is the binary search method. What is that binary search method? Let's see that on our 1D array. So our example was 3, 4, 5, 7. Oh, sorry, 3, 5, 4, 7. So let's apply our binary search method in it. So we need to find the LIS using the BS method, that is the binary search method. Now I have now we create an array. We have this array. We will check that this array, the last element of this array, is smaller than the current index. So is 3 smaller than the current greater than the current index? Yes, it is greater than the current index, so I will push it in. So the array will now become 3. We'll come to 5. Is it greater than the previous index? Yes, it is. So we'll put 3 comma 5. Now 4. No, 4 is not greater than it. So what we will do, lower bound basically. So we'll find the element which is just greater than equal to 4. So 5 was just greater than 4. So we'll replace 5 with 4. So the now the array is 3 comma 4. Now we'll come to 7. Is it greater than 4? Yes, it is. So the array will become 3 comma 4 comma 7. And then we'll return the size of the array. Okay. So the binary search method, what the binary search method do basically, let's say we have 3, 4, 5, 7, but then 2, 3, 5, 6, 8. So in DP, what we were doing, we were checking for, we are coming here, and then we'll let's say we come here, and then we'll look for all the elements behind it. Then we came here, we'll look for all the elements behind it. We came here, we look for all the elements behind it. That's created the time complexity to O of n square. Instead of doing that, what we will do, we will just look for the lower bound, that is the first greater element. So the array is 3, 4 came, so we'll put 4 here. 5 is bigger than it, so we'll put 5 here. 7 is bigger, we'll put 7 here, but 2 is not. So we'll find the element which is just greater than 2. So it will come here, and the array will become like this. Okay. Then again 3 came. Find the element which is just greater than 3, that is 4. So 2 comma 3. Then we'll find the element which is just greater than 5. So 5 is not greater than 7. So we'll find the element which is just greater than 5, greater than equal to 5. So we'll put 5 here. Then we'll come to 6. Is 6 greater than 7? No, it is not. So we'll find the element which is just greater than 6. So here. Then we'll find 8. 8 is, yes, 8 is. So we'll get 2, 3, 5, 6, 8. What does binary search do is basically it finds a position to put that particular element which is just smaller than the particular element. So by putting 2 here, we are paving way for all this element which can be a part of this subsequence, which can get attached to this element, but wasn't unable to attach to 3. Okay, you're getting what I'm saying? 3, we are putting this 2 in place of 3, so that we can create a possibility where we can put all these elements here. Okay, so what we'll do, we'll just find the element which is just greater than that particular element, and then we'll check for, is there any way of putting this element. So we'll follow this method, and because it is a sorted array, obviously we have a log n time complexity to find the lower bound, and hence the time complexity gets reduced from n square to n log n. Okay, the binary search approach is cool, is a very cool approach of solving LIS. Now, because binary search approach will do the work for n log n, now can we apply this into our envelope question? Let's see, we have this and sorted envelope question 2, 3, 5, 4, 6, 4, 6, 7. Okay, so now we try to do a binary search on it. Okay, but the problem arises, let's say we put 2, 3 here in our array, and then we'll check for 5, 4. If 5, 4 is greater than this, yes, I will say great, because 2 is smaller than 5, 4 is 3 is smaller than 4, so we'll put 5, 4. We check for 6, 4. Is it? No, it is not, because we need to check for both the conditions, right? We need to check for both the conditions, so we can't put it here. So we need to put 6, 4 in such a way that it paves a way. But let's say, because the array is infinitely long and there can be certain subsequence, there can be certain envelopes in which only this one can fall and not this one. There can be 6, 5, there can be 6, 6, sorry, 7, 5, 7, 6. Okay, so 6, 7 won't be able to fit into these envelopes, but this one can. So there can be existing those envelopes. So we need to put 6, 4 to, so that in future, if we encounter such an array, such an envelopes, we'll put them there. So where should we put 6, 4? We can't do a lower bound here. On what basis we'll do a lower bound? Can we do it on width? So the first element just greater than width? No, there is no. Okay, can we do it on height? For the first element just greater than equal to, oh, here it is. So should we put it here? Let's try to put it here. 6, 4. Okay, we put it here. 6, 7. Now 6, 7 is not able to fit into 6, 4. So we won't be able to put it anywhere. So we'll just find now we'll try to do a lower, because we did the lower bound on height. Let's do a lower bound on height again. We can't find any element. So there is a problem. We can't do a LIS on both of these element. We need to make sure that one of this dimension is constant. Okay, so we have sorted this according to the width, according to the first element. So let's make sure that the width is constant. Okay, so now the width is constant, so the width is out of picture now. So we're only looking at the height. We're only looking at the height. Okay, so the height, so LIS on 3, 4, 4, 7. Okay, so can we pick 3? Can we pick 3? So we pick 3. Is 4 greater than 3? Yes, it is. Is 4 greater than 4? No. Is 7 greater than 4? Yes. Oh, we get an array that is of 3 size. Hooray, we got our solution. But for the sake of it, let's check it on another example, where 4 is where instead of 3 there is 2, and instead of 4 there is 3. So it's 2, 4, 2, 3, 4, 7. But the width are same. That is, here the width is 2, here the width is 5, here the width is 6, and here the width is 6 again. So can we put 2 here? Okay, we did. Is 3 greater than 2? Yes, it is. Is 4 greater than 3? Yes, it is. Is 7 greater than 4? Yes, it is. So we get an array of 4 size. But we can't pick this because they both have the same width. We can't pick it, but the LIS did give us a solution here. And we are doing LIS on height. Mind it, I can do LIS on both of width or height. We just need to keep one of them as constant. Okay. So if both LIS is giving us this answer, why is this conflicting with the width? When the width are dissimilar, we can just do the LIS on this width. Okay, so we can just do the LIS on the heights. But when the widths are similar, we can't pick both of them, right? We can't pick both of them. So the LIS will fail. So what is the solution for this? Why don't we pick the element which has the highest height here? Why don't we pick the element which has the highest height and ignore all those other elements which have the same width but smaller heights? Okay, so let's just sort the array in that fashion. Try to sort that array in that fashion. Okay, so after sorting it, it will become 2, 2, 5, 6, 6, 2, 3, 7, 4. 7 has a greater height than 4, so we put 6, 7 ahead 6, 4. Okay, now try to do LIS on it. So the LIS will look like, LIS array will look like, we push 2. Is 3 greater than 2? Yes it is, so we'll push 3. Is 7 greater than 3? Yes it is, we'll push it. Is 4 greater than it? No way, it's not. So we get 2, 3, 7, which is our required subsequence. So can you see it what I'm saying? When we are creating, when we are saying that we are making sure that one dimension is following such order, we are making sure that one dimension is following such order, and we are creating the LIS on other dimension, we need to check for that point where the constant factor becomes equal. That is, where here the constant factor was the width, and if it becomes equal, we need to check what is the height of that particular envelope, because if they have similar width, we can't pick it, but we need to pick certain element. What can be that particular element? We need to pick that element which has the maximum height among all of them. So we'll sort our array in such a fashion that we are sorting it on the basis of certain dimension. We can sort it on with height also. For example, if we sort them on the basis of height, it will get like, so let's write the envelope coordinates. Let's dimension, not coordinates, 6, 7 and 6, 4. So if we sort them on the basis of height, it will be 2 will come here, 2, 2, 2 will come here, 5, 3 will come here again because 3 is greater than, and 6, 4 will come here, and 6, 7 will come here. And then we'll do the LIS on, width. So we'll put 2, 5 and 6, and we can't put 0. So we can also do, we can keep we can create one dimension as a constant factor, and if that constant factor conflicts, we will check the other dimension and sort that in the descending order. So we'll write our comparator function in such a manner that const comp, and it will consist of two vectors, let's say vector A and vector B. Basically this has two values, width and height, and this has two values, width and height. So we will say if A of 0 equal we have width at the 0 at next equals to B of 0, that is there is a conflict. So we will sort A of 1, so we'll return A of 1 greater than A of B of 1. Basically returning that is the height of the ath vector is greater than the height of the bth vector. But if there is no conflict, we'll just return simply B0 greater than A0. That is, we are sorting on the terms of width and in the ascending order, but if there is a conflict, we'll sort the height in the descending order. That's that for the comparator function. So we'll just create an array for storing all the height and applying lower bound on it, and then we'll just create the LIS. So that's that. Now let's code it. If you guys have done the LIS question previously, this might look easier to you, but if people who hasn't discovered LIS yet and people who haven't done questions on LIS, I will recommend them to solve certain questions on LIS. There is a typical question on LIS on LeetCode. You can just search LIS LeetCode. They will show you that particular question. You can solve that question. After solving that question, this question might look like a piece of cake to you after knowing what we have to do, because the main problem here is the sorting order, how we need to sort. Because when I saw this problem, the first thing which came to my mind was LIS, and I tried to implement my DP solution, but as I told you, the DP solution is an O of n square solution, so we can't apply it here. So what we will do, we will sort them in such a fashion that we can create our LIS on it. We can solve this question using LIS. So I will recommend you guys to see that particular question on LIS, and for reference you can either read articles from GFG on it, and then come to this question, and you will see a and you will see that you are understanding the question much more vibrantly and much more easily. So that's just my suggestion. Now let's code the question. So let's code it. Okay. So we'll first write our comparator function. It will be a boolean function because we need to return true or false, obviously. So bool static we need to give it a name. That would be, let's say, sort by W, because we're sorting according to width. So here we have two array int A and B. Then the condition is simple, that if A of 0 equal B of 0, then just return A of 1 greater than B of 1, else return B of 0 greater than A of 0. That is, if the width is similar, just sort the remaining array in the form of descending height. Okay, for all those width which have all those envelopes which have similar width. But if the width is not similar, we'll just return in the fashion of ascending order according to width. So we'll sort our array. It will be, let's give the name of the envelope as E dot begin, comma E dot end, and we'll pass a comparator function, that is sort by W. Then we need to know the size, so E dot size. We need to create an array also. That array will store all the element, and we have to, when we will do a binary search on that particular array, let's give it a name as array, and we'll push our first element in it. E of 0, 1, because we are doing LIS on height. So we'll do for int I equals to 0, I is less than n, I plus plus. If E of I, 1 is greater than ARR dot back, then we'll do just push it into it. E of I 1, else we'll need to find the lower bound. So auto it equal to lower bound comma that particular element, it is E of I, 1. The index will be int idx equals it minus arr dot begin Therefore, I did it minus ar dot begin because it will be an iterator, that the particular pointer. So we need to find that particular index where we will overwrite our element, that is arr idx. That this element is the just greater than equal to value. It has a just greater than equal to value than our particular height. So we'll say e of I comma 1, and then we'll return the size of the array. Oh, I'm writing it out of the function. Let's run it. Here it's passing both the test cases. Let's submit it. So this solution gets submitted. So it's showing that it is small. If it beats 55% solutions only, but let's check the solution which are at the top. Okay, they're doing the same thing. They are sorting it in the same order. They are creating LIS on lower bound. They are doing the same thing. Okay, so they are creating. They are also doing the same thing. That is, they are creating a constant factor on any of that particular dimension and then sorting it. Then doing LIS on the other dimension. That was it. I will still recommend to see more videos on LIS or read an article on it, and then try to solve this question. You will find it much easier. So that was it for today. I have solved this particular LC hard question. It was given in Google because DP solution on this particular question wasn't enough. So there is an optimal solution, and Google always asks for such question which we can optimize. That was the question from the series, and that was this question. Now we will cover bulls and cows, counting nice subarrays, both of these in one particular video. Because I don't think any other question is that particular hard, so we can combine two questions in one particular video. Then we will start with our Walmart series. I think we need to complete Goldman Sachs at the end, I should start with Goldman Sachs because that will keep things in order. So after completing Microsoft, I will move on to Goldman Sachs, then Walmart. So that was it for today, guys. I hope you like the video. Please like and subscribe and share it if it is possible. So thank you. See you again in another one.